Okay, so my second lesson to introduce differential equations is talking about Newton's cooling or warming law. So basically, this is another law that is going to be really simple from the point of view of differential equations. Newton's, let's say, cooling, also it works for warming law, as we will see. And this is another very simple model of differential equation, but it's also like really interesting to introduce it so we can get used to how actually differential equations are important, just in case that someone was wondering what they are for. So Newton's law, basically what it says, it's the following thing, that the gaining or loss of heat of certain body in outdoor, indoor, whatever setting at a different temperature of that of the body is going to be proportional to the difference between the temperatures between the body and the setting, the ambience. So the gain or loss of heat of certain body in an indoor setting at a different temperature of that of the body is proportional to the difference in temperature between the body and the ambient temperature. So this was Newton's claim. So what we have to do is to try to write this claim in terms of a differential equation. And it's also pretty easy and straightforward. So basically, let's introduce some variables. So let's call t, which is going to be a function of t, because obviously it's going to be changing with time. This is going to be the temperature of our body. I mean, not our body, like the body we're considering. Temperature of body under consideration. And we're gonna consider Tm as the temperature of the surroundings. And this one is gonna be a constant because it's not gonna be changing. It's gonna be that the surroundings are supposed to be at a constant temperature. So this is a constant temperature of the surroundings. Okay, so let me call T0 is going to be the initial temperature of the body that we're studying. And this is obviously going to be a constant too, because it's an initial number, okay? And well, so now with these variables, we can introduce our Newton's cooling or warming law. Or heating, I don't know, you can call it warming or heating law, any of the two, I guess. So it says that the temperature of the body under consideration, which is actually a function of T, Bear in mind here that t is going to be a dependent variable. And bear in mind here that t, the time, is going to be the independent variable. I think it's really, really important to check this out, because when you're integrating differential equations, sometimes they will give you a differential equation and you will really know which one is the independent and which one is the dependent. So that's the first thing you have to figure out, because you're going to make lots of variable changes, not in this problem, but in forthcoming classes, we'll be making lots of variable changes, and we really have to keep track on which one is the dependent variable and which one is the independent, because otherwise it can be a real mix. So what the law says is that the differential of the temperature of the object with time, it's proportional, let's say R to be this constant of proportionality, to the difference of temperature between the body under consideration and the temperature of the surrounding ambience. So R is going to be constant, and R can actually be positive or it can be negative. So as you will see, if R happens to be negative, we will have cooling of the body. And if R happen to be positive, we will have warming or heating up the body. Okay, so well, let's set it as R, and then we'll see what happens with some specific examples. So basically, this is a first order differential equation as well. It's a very simple equation. As you can see, it's one of those equations that we call inseparable variables, because as you can see, again, you can put to a side all the dependence on the temperature, and you can put all the dependence of time in the right-hand side, because remember that this is a constant. And remember that this is a constant too. So that basically means that on the left-hand side, it's all dependent on the temperature. On the right-hand side, it's all dependent on T. So this is another differential equation of first order with separate variables. You know, it's very interesting as we proceed that we'll see that what we're going to try to do in the whole course is to look for some kind of variable changes, so we reach a differential equation that is separable in variables, so we can integrate it. So that's basically what differential equations courses are for, to learn some techniques in which we can put the differential equation in such a form that the variables are separate and we can integrate. So we just have to look for the primitive of the integral that we come up with. So yeah, well, if we rewrite the equation, then we have this one, and we can actually integrate from a time zero, T0 to T, and a temperature T0, which is the initial temperature of the body, to a temperature T. So this is straightforward. Just look at the left-hand side. It's just the logarithm. I'll use the Neperian logarithm because this is a constant. So we have the derivative in the numerator. So basically, it's just the Neperian logarithm of t minus tm, and the limits are t0 and t. And here on the right, we'll have r times t minus t0. If we consider t0 to be the initial time and equal to 0, we can just write that RT equals the logarithm of T minus T M minus the logarithm of T0 minus Tm. But basically we can rewrite this like this. And if we want to take out T, which is the variable that we need, we just have to take the exponential. So T minus Tm is going to be T0 minus Tm exponential RT. And then the T that we're looking for is Tm plus T0 minus Tm and the exponential. So this expression is basically the integration of the law of Newton, okay? So this is it, and let's call it Newton's cooling or warming law. Okay, I stopped it for a second.
I'm sorry, I have to get my shoes.
Yeah, it's okay. Where are you going?
To work.
Oh, you have class in the morning?
I have class at 1, but I have to get there a bit early to meet with this geisha.
Ah, I thought you only had class at 7 too today.
No, that's just for this week. That's only Tuesday and Thursday.
Oh, so what kind of classes you have today?
Huh?
What classes do you have today?
Today Monday I had 3 classes. Today I have 2 of those 3 classes because one of the classes is only a once a week thing.
Mm-hmm.
And then tomorrow I just have the 1 class.
Okay. Wait, I'll stop this.
Sorry.